The thing that makes quantum computing simultaneously exciting and unsettling is not just that it threatens old encryption. It is that the same underlying physics enabling that threat also enables breakthroughs of extraordinary positive value. Consider drug discovery. The pharmaceutical development pipeline is slow and expensive by any measure. Developing a single new drug from initial research to clinical approval takes an average of over a decade and costs billions of dollars, with a failure rate that exceeds 90% for compounds entering human trials. A significant part of this failure comes from incomplete modeling. Researchers cannot fully simulate how a drug molecule will interact with its biological target, the protein or enzyme it is meant to affect, because the quantum mechanical behavior of electrons in molecular binding interactions is too complex for classical computers to model accurately at scale. Quantum computers designed for chemical simulation could change this dramatically. A quantum processor running quantum simulation algorithms would not be approximating quantum behavior from the outside. It would be representing the quantum states of electrons directly, tracking superpositions and entanglements in the molecule with precision that classical hardware fundamentally cannot achieve. This means more accurate predictions of which molecules will bind effectively to which targets, which compounds will have unintended toxic effects, which structural modifications would improve a drug's efficacy. This is not a speculative possibility reserved for the distant future. Research teams at pharmaceutical companies and universities are already developing quantum algorithms for molecular simulation. IBM and Google are partnering with drug companies to explore near-term quantum applications. The timelines for fully fault-tolerant quantum computation are uncertain, but the direction is clear. The same simulation advantage applies to materials science. Designing new superconductors materials that conduct electricity with zero resistance at practical temperatures could revolutionize energy transmission and storage. But identifying which material structures would exhibit superconductivity at higher temperatures requires simulating electron interactions of extraordinary complexity. Quantum computers are specifically suited for this kind of simulation, and progress in room temperature or near room temperature superconductors could have cascading effects on everything from power grids to electric vehicles to medical imaging hardware. Quantum computing also has profound implications for optimization problems. Many real-world challenges, logistics routing, financial portfolio balancing, supply chain management, traffic flow optimization, protein folding are what mathematicians call no-problem hard or no-problem complete problems. For large instances, classical computers cannot find the exact optimal solution in reasonable time. They use heuristics and approximations. For some applications, this is fine. For others, like designing optimal drug delivery systems or optimizing the routing of thousands of delivery vehicles, getting closer to the true optimum has enormous practical value. Quantum optimization algorithms, including the quantum approximate optimization algorithm and variational quantum eigensolvers, offer approaches to these problems that may outperform the best classical methods for specific problem structures. The theoretical advantages here are more nuanced than the dramatic speedup of Shor's algorithm. Quantum optimization does not always guarantee exponential speedup over classical methods, but even polynomial improvements on hard optimization problems translate to significant real-world gains. Now here is where the picture becomes more philosophically complicated, and it is worth sitting with this discomfort rather than skipping past it. Quantum computers are not magic. They are not universal problem solvers. They are not, as they are sometimes portrayed in popular coverage, machines that will simply calculate everything faster than classical computers. The speed up they offer is specific, algorithmically precise, and limited to problem classes, where the mathematical structure of quantum computation provides a genuine advantage. For most of what your laptop does right now, writing documents, browsing the web, running spreadsheets, streaming video, a quantum computer offers no advantage whatsoever. In fact, for those tasks, classical computers are faster, more efficient, and far easier to manufacture and operate. Quantum computers are not replacements for classical computers. They are specialized instruments for a specific class of hard problems where quantum mechanical properties provide a structural computational advantage. This distinction matters because the hype around quantum computing regularly outpaces the reality in ways that can mislead both public understanding and investment decisions. Companies have announced quantum supremacy milestones, demonstrations that a quantum processor performed a specific computation faster than the best classical supercomputer. But those benchmark computations were carefully chosen to be exactly the kind of task quantum processors excel at, not necessarily tasks with immediate practical applications. The gap between demonstrating quantum supremacy on a contrived benchmark and running Shor's algorithm on real cryptographic keys is enormous and involves solving hard engineering problems that are still being worked on. This is not a reason for pessimism. It is a reason for clarity. Quantum computing is a genuine scientific revolution in progress. Its potential impact on cryptography, drug discovery, material science, and optimization is real and well supported by decades of theoretical work and growing experimental evidence. But that potential will be realized through specific, carefully engineered solutions to specific, well-defined problems, not through a single general-purpose quantum machine that solves everything. Understanding the limits of quantum computing requires understanding something deeper about computation itself. And this brings us to what is perhaps the most philosophically unsettling aspect of the entire quantum computing story: the relationship between complexity and reality. Let us go back to coins, specifically to coin flipping. Flip a coin once, 2 possible outcomes, heads or tails. Flip it twice, 4 possible sequences. Flip it 10 times, 1,024 possible sequences. This growth is exponential. Each additional flip doubles the number of possible outcomes. For 66 flips, the number of possible sequences exceeds the number of atoms in the observable universe. For 266 flips, the number of possible sequences is a number so large that if every person on Earth, equipped with a computer counting 1 billion sequences per second, began counting at the moment of the Big Bang, they would not have finished counting yet. This is not a rhetorical point about big numbers. It is a fundamental observation about the structure of combinatorial complexity, and it is directly connected to why certain problems are computationally hard. Cryptographic security, for instance, is built on this combinatorial explosion. RSA encryption works because factoring large numbers is, on a classical computer, essentially a combinatorial search problem. The space of possible factors grows exponentially with the size of the number. Without a shortcut, without an algorithm that exploits hidden mathematical structure to avoid searching the full space factoring, is intractably hard. Shor's algorithm is a shortcut. It exploits the periodic structure of modular arithmetic to transform the factoring problem into a period-finding problem. And quantum mechanics allows period finding to be done efficiently using quantum Fourier transforms. The quantum speedup is real, but it is a shortcut that works because of specific mathematical structure in the factoring problem. Problems that lack that kind of exploitable structure do not benefit from Shor's approach. The deep lesson here is that computational difficulty is not just about processing speed. It is about the mathematical structure of problems. Classical computers are powerful because many real problems have exploitable structure patterns, regularities, compressions that allow efficient algorithms to work. Quantum computers add a new layer of exploitable structure, quantum mechanical phenomena. But the problems that resist both approaches are those with no such structure at all, problems that require genuinely exhaustive search over exponentially large spaces. Here's where the philosophical knife edge cuts deeper. When physicists say quantum computers can represent more states than there are particles in the universe, they are describing the mathematical dimensionality of the quantum state space, the Hilbert space of 300 qubits. But they're not saying that a quantum computer actually stores or processes all those states simultaneously in some classical sense. What it does is maintain a quantum superposition that evolves according to quantum mechanical rules, and carefully designed algorithms exploit that evolution to produce useful outputs. The quantum computer does not, in any simple sense, think about all possibilities at once and then announce the answer. The process is more subtle. The quantum state evolves. With interference affects the quantum analog of waves, adding or canceling, amplifying the probability of correct answers and suppressing the probability of wrong ones. At the end, a measurement collapses the quantum state into a classical answer. The power comes from the interference, from the way quantum amplitudes behave mathematically during the computation. This is why writing quantum algorithms is hard. You are not just programming a computer to do things faster. You are designing a quantum process that, through interference, steers probability amplitudes toward desired outcomes. The algorithm design requires deep understanding of both the problem structure and the mathematics of quantum mechanics. It is a creative challenge, unlike classical programming. The difficulty of this challenge is part of why the universe of problems with known quantum speedups is more limited than popular accounts often imply. Shor's factoring algorithm, Grover's search algorithm, and quantum simulation algorithms are the major known cases where quantum computers provide substantial advantages. Researchers are actively working to expand this set, but the expansion happens through mathematical ingenuity, not through brute hardware scaling. Now, let us confront the deepest question that all of this raises. Not about computers, about reality. Quantum mechanics is the most precisely tested physical theory in human history. Its predictions match experimental measurements to over 10 significant figures in some cases, a level of accuracy unmatched anywhere else in science. It correctly describes the behavior of electrons, photons, atoms, and the interactions between them. Every modern technology that depends on precise understanding of matter at small scales, semiconductors, lasers, MRI machines, atomic clocks, ultimately rests on quantum mechanics. But quantum mechanics describes reality in a way that is deeply strange. Particles exist in superpositions of multiple states simultaneously until they are measured. The act of measurement collapses those superpositions into definite classical outcomes. Entanglement allows two particles separated by vast distances to behave as a correlated system, such that measuring one instantly defines properties of the other. These features are not interpretive difficulties. They are not philosophical debates about language. They are experimentally confirmed properties of nature. Bell test experiments, conducted with increasing rigor since the 1960s and refined with loophole-closing precision in recent decades, have definitively shown that quantum correlations cannot be explained by any theory based on local hidden variables. The universe at the quantum level is genuinely non-local, genuinely probabilistic, and genuinely does not assign definite values to unmeasured quantities. Quantum computers are machines built to run on these features. They do not just use quantum effects incidentally, the way classical transistors exploit quantum tunneling in a limited way. Quantum computers are explicitly designed around superposition and entanglement as computational resources. Building them requires engineering at the level where these strange features of nature are the primary design considerations, not background physics to be managed. There is something profound about this that often gets lost in the coverage of quantum computing milestones and qubit counts. We are building information machines out of the fabric of reality at a level where reality behaves according to rules that have no classical analog. The information is not stored in the positions or velocities of particles in any classical sense. It is encoded in quantum amplitudes, in the wave-like probability distributions that describe where particles might be and how they might behave. And here is the implication that deserves direct attention. We do not fully understand why quantum mechanics works. We have equations, Schrödinger's equation for non-relativistic quantum mechanics, the Dirac equation for relativistic electrons, quantum field theory for the full standard model of particle physics, and these equations produce predictions that match experiment with extraordinary precision. But the interpretation of what those equations mean, what they say about the nature of reality, about what is really happening when particles are in superposition, about what it means for measurement to collapse a quantum state, remains genuinely contested among physicists. The Copenhagen interpretation says that asking about the state of a quantum system before measurement is meaningless. The system does not have a definite state until you measure it. The many worlds interpretation says measurement does not collapse anything. Every possible outcome occurs, each in a branching version of reality. Pilot wave theories say particles have definite positions at all times, but those positions are guided by a real quantum wave that propagates through all space. Cubism says quantum states are not descriptions of external reality, but expressions of an agent's beliefs about future experiences. These are not fringe ideas. They are serious positions held by serious physicists, and they make different predictions about subtle experimental questions that are only now becoming testable as quantum technology advances. Building quantum computers at larger and larger scales may eventually force some of these interpretive disputes toward experimental resolution. A sufficiently large quantum computer maintaining coherence across millions of qubits would provide a laboratory for probing questions about the nature of quantum measurement that cannot be addressed with any smaller system. This is one of the reasons quantum computing sits at such a strange intersection of engineering and fundamental science. It is not just a technology. It is an experimental apparatus for probing the nature of reality at scales and complexities that have never been accessible before. Consider the question of quantum computational advantage at scale. As quantum computers grow larger, the question of when quantum mechanics transitions to classical behavior, sometimes called the quantum to classical boundary or the measurement problem, becomes practically relevant. Real quantum processors experience decoherence. They leak quantum information into their environments, causing quantum superpositions to degrade into classical probabilistic mixtures. Engineers combat this with error correction, with increasingly sophisticated qubit designs, with ever more elaborate shielding. But each additional qubit and each additional gate operation multiplies the opportunities for decoherence to occur. At some scale, the engineering challenge of maintaining quantum coherence may become exponentially harder in ways that offset the exponential advantage of the quantum computation itself. Nobody knows where that boundary is. It is one of the central open questions in quantum computing research. Optimists believe that error correction techniques will scale well enough that large fault-tolerant quantum computers are feasible. Skeptics question whether the engineering challenge will prove tractable for qubit counts large enough to run practically useful algorithms on realistic problem instances. The honest answer is that we do not yet know. The physics says quantum computational advantage is real and well defined. The engineering says building hardware that reliably realizes that advantage at scale is hard in ways that are not yet fully understood. Both things are true simultaneously. This uncertainty is itself scientifically valuable. It drives research in error correction theory, in qubit design, in material science for quantum hardware, in algorithms that can extract useful results from imperfect quantum processors, what researchers call noisy intermediate-scale quantum devices, or NISQ computers. Current quantum processors fall into this NISQ regime. Too noisy for full fault-tolerant computation, but large enough and controlled enough to run short quantum circuits with some degree of coherence. Researchers are exploring what is achievable in this NISQ era while working toward the fault-tolerant machines that would enable the full range of quantum algorithmic advantages. The work happening at the intersection of these challenges is producing knowledge that extends far beyond quantum computing itself. Research into decoherence and quantum error correction has deepened understanding of the fundamental physics of open quantum systems. Research into qubit hardware has driven advances in superconducting materials, atomic physics, photonics, and semiconductor fabrication. Research into quantum algorithms has produced new mathematical tools applicable to classical computing, cryptography, and information theory. Science and technology do not develop in straight lines. The pursuit of one goal reliably produces unexpected knowledge in directions no one initially anticipated. The decades-long effort to build practical quantum computers has already changed our understanding of information, complexity, and the physical nature of computation. Whatever the final shape of quantum technology turns out to be, that knowledge does not disappear. Return, for a moment, to the coin flip. 266 flips. More possible sequences than atoms in the observable universe. The point of that exercise is not really about coins. It is about what the universe contains. Most of what is mathematically possible, most of the configuration space of any sufficiently complex system will never be explored. Not because of limits on computing power, because the universe itself, with all its atoms and all its time, is finite in a way that makes most of that space permanently out of reach. Classical computers navigate this by sticking to the problems that have exploitable structure. Quantum computers extend the reach by adding quantum mechanical structure to the toolkit, but neither escapes the fundamental fact that the mathematically possible vastly exceeds what is physically computable. The universe is more complex than any conceivable machine built within it. This is not a pessimistic conclusion. It is a clarifying one. It means there will always be open problems. It means the pursuit of better computation, quantum, or otherwise, is not heading toward an end state where everything is calculated and nothing is unknown. It is heading toward better tools that push the frontier of what is knowable, while the universe continually reveals that the frontier extends further than the tool's reach. There is a deep intellectual honesty required when thinking about quantum computing's limits. We simplify not because reality is simple, but because simplicity is what we can handle. We solve not the hardest problems, but the problems we have learned how to solve. The development of quantum algorithms is itself a creative act of simplification, finding the problems whose structure quantum mechanics can exploit, designing circuits that steer quantum probability amplitudes toward useful outputs, discovering the mathematical shortcuts that turn exponential classical hardness into tractable quantum computation. Quantum computers will not simulate all of nature. They will not solve all hard problems. They will not render all cryptography obsolete overnight. What they will do, what they are already beginning to do, is expand the class of problems that are solvable in practice, in ways that have real consequences for medicine, materials, science, communication security, and our understanding of quantum physics itself. The science of quantum information is young. Peter Shor's algorithm is only 3 decades old. Quantum error correction as a systematic theory only emerged in the mid-1990s. The first experimental demonstration of a quantum algorithm on a real device came in 1998. The first systems with enough qubits to demonstrate quantum supremacy on any task appeared only in the last few years. By the standards of transformative technologies, this is still early morning. The development of classical computing from Turing's theoretical machine in 1936 to the personal computer took 4 decades. From the personal computer to the internet age took another 2. Quantum computing is at an earlier and more uncertain stage of that development arc, facing harder physical challenges and requiring more fundamental scientific progress alongside the engineering. What researchers still do not know is extensive. They do not know the exact point at which fault-tolerant quantum computation becomes feasible in practice. They do not know which qubit modality, superconducting circuits, trapped ions, photons, topological qubits, neutral atoms, nitrogen vacancy centers in diamond will prove most capable of scaling to the millions of physical qubits estimated to be needed for practically useful fault-tolerant quantum computation. They do not know the full landscape of problems for which quantum algorithms provide meaningful advantages over the best classical methods. They do not know whether the quantum to classical transition will pose unexpected obstacles at scales larger than currently accessible. And underneath all of this, the foundational physics question persists. Quantum mechanics predicts a world that is fundamentally probabilistic, non-local, and in which measurement plays a physically constitutive role. We have equations that describe this world with extraordinary precision. We do not have consensus on what those equations mean. Building quantum computers at increasing scales will test those equations in regimes of complexity that have never been accessible experimentally. The machines might answer questions that the founders of quantum mechanics could only argue about philosophically. That may be the most remarkable thing about quantum computing. It is not just an application of quantum physics. It is a probe of quantum physics. The machines we build to exploit the strangeness of the quantum world will, in doing so, reveal more of that strangeness. Every qubit added to a coherent quantum processor is another window into a level of reality that classical intuition cannot reach. We are at the beginning of that exploration. The mathematical foundations are solid. The physical principles are well established. The engineering challenges are real and partly unresolved. The implications for cryptography, for medicine, for materials, for our understanding of information and reality are genuinely profound. The next decades of quantum computing research will not be a story of machines solving all problems. There will be a story of very smart people pushing very carefully at the boundary between what is known and what is possible, armed with mathematical tools that are only a few decades old and hardware that is only a few years away from demonstrating real practical advantage. The frontier is open, the questions are real, and the answers, when they come, will change not just what we can compute, but what we understand about the nature of the universe we are computing within. If you found these ideas as compelling as they deserve to be, consider supporting the work of explaining them. There is always more of this kind of exploration worth doing, and sharing content like this with others who think carefully about science and technology, is exactly how these conversations reach the people who need them most. Let us take a step back and examine the mathematical structure that makes quantum computing possible, because understanding it properly changes how you see the entire field. Classical computing rests on Boolean logic. Every operation and, or not, exclusive, or maps inputs that are either 0 or 1 to outputs that are either 0 or 1. Gates combine these operations into circuits. Circuits combine into processors. Processors run instructions. And from this foundation, every classical program ever written emerges. The logic is deterministic. Given the same inputs, a classical circuit always produces the same output. If you run a classical algorithm twice on the same data, you get the same answer both times. This determinism is not just convenient for programmers. It is fundamental to the way classical computers are engineered. Engineers build in redundancy, error detection, and fault tolerance precisely because they can compare expected deterministic outputs with actual measured ones and flag discrepancies. Quantum logic works differently at every level. Instead of bits, quantum computers use qubits. Instead of definite 0 or 1, a qubit before measurement exists in a quantum state that is a superposition of 0 and 1, described by two complex numbers called amplitudes. The squared magnitudes of those amplitudes give the probabilities of measuring 0 or 1 respectively. The amplitudes themselves can be positive, negative, or imaginary, and this is crucial because it means they can interfere constructively or destructively, like waves. Quantum gates manipulate these amplitudes. A Hadamard gate takes a qubit that starts in a definite 0 state and puts it into an equal superposition of 0 and 1, both outcomes equally likely. A phase gate shifts the amplitude of one component without changing the probability of either outcome. A CNOT gate entangles two qubits, making the state of one depend on the state of the other in a way that has no classical analog. The power emerges from how these gates combine. A quantum circuit that operates on 300 qubits is transforming a quantum state that lives in a Hilbert space of dimension 2 to the power of 300. Each gate transforms this high-dimensional vector according to precise unitary transformations. The algorithm designer's job is to choose gates so that by the end of the circuit, the computational basis states corresponding to wrong answers have had their amplitudes reduced by interference, while the states corresponding to correct answers have had their amplitudes amplified. At the end of the circuit, measurement collapses the quantum state to a single classical outcome. If the algorithm was designed correctly, the most probable outcome corresponds to the right answer. Running the circuit multiple times and taking the most common result gives you high confidence in the correct answer, even though any single run is probabilistic. This probabilistic nature is not a weakness. It is a feature that emerges from the mathematics. Shor's algorithm, for instance, does not deterministically produce the prime factors of a large number on a single run. It probabilistically produces a number that, with very high probability, allows you to calculate the factors using a few additional classical steps. The quantum computation does the hard exponential time part. Classical post-processing does the rest. The combination is efficient. Neither alone is. Understanding this interplay between quantum and classical computation is important because it changes the mental model of what quantum computers are for. They are not standalone replacements for classical systems. They are quantum coprocessors, specialized processors handling the parts of problems where quantum algorithms provide advantage, feeding results to classical processors that handle the rest. The most practically useful quantum computing architectures will likely be hybrid systems, with quantum processors handling molecular simulation steps or optimization kernels, while classical processors handle data management, output processing, and algorithm control. IBM, Google, and other companies building quantum hardware are already developing these hybrid architectures. Quantum cloud services allow researchers to submit quantum circuits for execution on real quantum hardware remotely, just as they submit classical computations to cloud computing platforms. The tooling for writing quantum programs, frameworks like Qiskit from IBM and Cirq from Google, is maturing rapidly. Graduate students today write and run quantum algorithms on real hardware as a routine part of their research, something that was unimaginable 15 years ago. This accessibility matters for the development of quantum algorithms. One of the bottlenecks in quantum computing has always been the small community of people with a specialized mathematical background to design quantum algorithms. Making quantum hardware broadly accessible lowers the barrier to entry and brings more minds to the problem of finding new applications and new algorithmic approaches. The history of classical computing suggests this kind of broad access is transformative. Most of the important applications of classical computers were discovered by people who were not computer scientists, applied to domains their designers never anticipated. Let us think more carefully about what it means for a quantum computer to represent a state that contains more information than the observable universe can store. The statement is mathematically precise, but easily misunderstood. A quantum state on 300 qubits is a vector in a complex vector space of dimension 2 to the power of 300. Specifying this vector exactly requires writing down 2 to the power of 300 complex numbers. The number of atoms in the observable universe is approximately 10 to the power of 80. 2 to the power of 300 is approximately 2 times 10 to the power of 90, which is 10 billion times larger. So yes, the exact description of a 300-qubit quantum state contains more information than could be stored in every atom in the universe, if each atom stored 1 bit. But the quantum computer does not actually store all that information explicitly. What it stores is the quantum state itself, encoded in the physical properties of 300 quantum systems, the correlations between them, and the way those correlations evolve under the quantum gates applied to them. The information is not sitting in a classical memory array with 2 to the power of 300 entries. It is encoded in the quantum amplitudes of the physical system, which evolve according to Schrödinger's equation in a way that is exponentially richer than any classical description. This is precisely the insight that makes quantum simulation so powerful. When you want to simulate a quantum system, a molecule, a material, a photonic network on a classical computer, you have to store those exponentially many amplitudes explicitly, which becomes impossible for even modest system sizes. When you simulate a quantum system on a quantum computer, the quantum system itself is the storage medium. The simulation runs naturally. The exponential overhead disappears because you are not translating quantum behavior into classical bits anymore. You are letting quantum behavior compute quantum behavior directly. This is what Feynman understood in 1981. Not just that quantum computers would be faster, that they would be natural simulators for quantum systems in a way that classical computers are fundamentally not. The practical implications for chemistry and biology are worth developing carefully. Every chemical reaction involves electrons rearranging themselves among atoms. The energy barriers between molecular configurations, the electronic structure of transition states, the binding affinity between a drug and its protein target, all of these are determined by quantum mechanical interactions among electrons and nuclei. Classical computers handle this by making approximations. Density functional theory, one of the most widely used quantum chemistry methods, approximates the true quantum electron density with a functional that captures the main features at a manageable computational cost. These approximations work well for many molecules, but fail for systems with strong electron correlation situations where the behavior of each electron is deeply entangled with the behavior of all the others. Strong correlation is precisely the regime where quantum simulation provides the most dramatic advantage. And strong correlation is exactly what occurs in the transition metal complexes that serve as the active sites of enzymes in the high-temperature superconductors whose mechanism remains not fully understood, and in many of the molecular systems most relevant to medicine and clean energy technology. A quantum computer capable of accurately simulating these systems would not just speed up existing chemistry research, it would open entire areas of molecular science that are currently inaccessible. The nitrogen fixation problem offers a concrete illustration. Nitrogen makes up about 78% of the atmosphere. Plants need nitrogen to grow. But atmospheric nitrogen is molecular dinitrogen, with a triple bond so strong that most plants cannot access it. Agriculture depends on the industrial Haber-Bosch process to convert atmospheric nitrogen into ammonia, which plants can use. The Haber-Bosch process requires temperatures of 400 to 500 degrees Celsius and pressures of 150 to 300 atmospheres, consuming about 1 to 2% of global energy production. It is a massive industrial operation with a large carbon footprint. In nature, certain bacteria fix nitrogen at room temperature and atmospheric pressure using an enzyme called nitrogenase. The active site of nitrogenase contains an iron-molybdenum cluster whose quantum mechanical behavior controls the catalytic process. Understanding exactly how nitrogenase works would open the door to designing synthetic catalysts that replicate it, potentially enabling nitrogen fixation at ambient conditions with a fraction of the energy cost. This would transform global agriculture and significantly reduce the energy and carbon intensity of food production. Classically simulating the iron-molybdenum cluster of nitrogenase, even with the best approximations, is beyond current capability. The system has approximately 120 molecular orbitals that must be treated quantum mechanically, requiring a quantum simulation of over 100 qubits with sufficient coherence and gate fidelity to run the relevant algorithms. That is beyond current hardware, but within the range that researchers project for the next generation of fault-tolerant quantum processors. This single application understanding nitrogenase justifies a substantial fraction of the global investment in quantum computing research. Similar arguments apply to understanding high-temperature superconductivity. The cuprate superconductors, discovered in 1986, can conduct electricity without resistance at temperatures above the boiling point of liquid nitrogen, far warmer than conventional superconductors, but still well below room temperature. The mechanism underlying their superconductivity involves strongly correlated electrons in a copper-oxygen plane, and despite decades of intensive theoretical and experimental work, no completely satisfactory theoretical explanation exists. Quantum simulation could provide the computational tools needed to crack this long-standing problem. A working room-temperature superconductor, enabled by that understanding, would transform energy transmission, making it possible to move electricity across continents with near-zero loss. The trajectory of quantum hardware is not simply a matter of adding more qubits. It is a matter of adding more high-quality qubits units with low enough error rates that quantum error correction schemes can reduce errors further rather than amplifying them. This distinction between physical qubit counts and logical qubit counts is crucial. A logical qubit is a fault-tolerant unit of quantum information protected by error correction. A physical qubit is the actual hardware component with all its imperfections. Depending on the error rate, anywhere from hundreds to thousands of physical qubits may be required to realize a single logical qubit with error rates low enough for long computations. This overhead is why estimates for the physical qubit count needed to run Shor's algorithm on realistic cryptographic keys run into the millions. Current leading systems have hundreds to thousands of physical qubits. The gap is large, but it is closing, and the research progress on error rates, connectivity, and gate fidelity is steady. Milestone demonstrations that would have seemed impossible a decade ago are now routine. The engineering challenge is immense, but not obviously intractable. Different qubit technologies are advancing along different trajectories. Superconducting qubits, the technology used by Google and IBM, we are fast and scalable in terms of fabrication, but sensitive to thermal noise and require operation at temperatures very close to absolute zero, about 15 millikelvin, or about 273 degrees Celsius below the freezing point of water. Trapped ion qubits, used by companies like IonQ and Quantinuum, have extremely low error rates and long coherence times, but are slower to operate and harder to scale because they rely on manipulating individual atoms held in electromagnetic traps. Photonic qubits use photons as the quantum information carriers and can operate at room temperature but face challenges in achieving deterministic photon-photon interactions needed for 2-qubit gates. Neutral atom qubits are an emerging modality showing rapid improvement, offering the possibility of highly connected large-scale arrays of atoms manipulated by precisely targeted laser beams. Each of these technologies has different strengths and different paths to scalability. It is unlikely that a single modality will dominate all applications. Just as classical computing evolved to include CPUs, GPUs, FPGAs, and application-specific chips for different computational tasks, quantum computing will likely develop an ecosystem of different qubit technologies, optimized for different problem types and scales. What is striking about the current moment in quantum computing is the convergence of multiple necessary elements. The theoretical foundations have been developed. The algorithmic toolkit, while still limited, is real and growing. The hardware is advancing steadily across multiple competing technologies. The error correction theory is sufficiently mature that the path to fault tolerance is mapped out in principle, even if the engineering execution remains difficult. And the ecosystem of researchers, engineers, companies, and government programs investing in quantum computing has reached a scale that makes rapid progress substantially more likely than it was even a decade ago. This convergence did not happen by accident. It resulted from sustained investment in foundational science, the kind that does not have an obvious application when it begins. The theoretical framework for quantum computing emerged from physicists asking basic questions about information, measurement, and computation in quantum systems. The experimental tools needed to manipulate individual atoms, photons, and electrons at the quantum level were developed for fundamental physics experiments, not for computing. Error correction theory emerged from the intersection of quantum physics and classical information theory, two fields not obviously connected until researchers made the connections explicit. This history carries a lesson that extends beyond quantum computing. The technologies that have most transformed human civilization, computing, the internet, modern medicine, renewable energy, emerged from basic research that was not obviously practical when it began. Quantum mechanics itself, the theory that underlies quantum computing, was developed in the 1920s to explain atomic spectra. Nobody building that theory was thinking about computing. They were trying to understand why electrons do not spiral into atomic nuclei. That question led to Schrödinger's equation, which led to quantum chemistry, which led to the design of transistors, which led to classical computers, which led to the digital age. Quantum computing is now at the beginning of a similar chain. The same equations being exploited for quantum processors have applications in materials, science, chemistry, biology, and fundamental physics that feed back into one another in ways that are not fully predictable. The technology is not just a product. It is a scientific instrument that will enable new science, which will enable new technology, in a cycle that is only beginning. The science fiction vision of a quantum computer is a black box that solves everything unbreakable encryption, instantly cracked, all molecular structures instantly determined, all optimization problems instantly solved. The reality is more nuanced and in some ways more interesting. Quantum computers will solve specific hard problems that classical computers cannot. They will create specific vulnerabilities in systems that have not migrated to quantum-resistant cryptography. They will enable specific discoveries in chemistry and materials that are not accessible to classical simulation. These are not incremental improvements over classical computing. They are qualitative changes in what is computationally possible, but they are also bounded changes, operating within the fundamental limits set by computational complexity theory, by the engineering constraints of physical qubits, and by the mathematics of what quantum algorithms can and cannot do efficiently. The universe's complexity remains vastly greater than any machine's reach. 266 coin flips produce more possible sequences than any quantum computer built within the universe could enumerate. The space of what is possible dwarfs the space of what is computable, and the space of what is computable dwarfs what will ever be computed in practice. This is not a limitation to lament. It is the permanent condition of finite minds in an infinitely complex universe, finding more and more sophisticated tools to push the boundary of the knowable, while the boundary keeps moving. Quantum computing pushes that boundary in specific, important, and genuinely transformative directions. Understanding which directions, and why, and at what cost, and over what time scale, is the work of careful science, the kind that resists hype in both directions, neither dismissing the technology as overpromised, nor inflating it into a magical solution. The most honest thing that can be said about quantum computing today is this: the theoretical case for its power is settled. The experimental demonstrations of quantum phenomena, exploitable for computation, are real. The engineering path to practically useful, fault-tolerant quantum computers is visible, if not yet traveled. The applications in cryptography, chemistry, and optimization are well defined and consequential, and the timeline remains uncertain enough that anyone predicting a precise date for commercial quantum advantage on real problems should be treated with appropriate skepticism. Science rarely announces its revolutions with clear dates and simple milestones. Quantum computing is changing the landscape of what is computationally possible, one paper, one experiment, one qubit at a time. The transformation is real. Its full shape is still being revealed, and the physics that makes it possible is the same physics that tells us reality at its deepest level is stranger and more mathematically rich than classical intuition can grasp. That strangeness is not a bug. It is a resource. Quantum computing is the first technology built explicitly to exploit it. There is a concept in quantum information theory called quantum entanglement that deserves far more careful attention than it typically receives in popular accounts. Entanglement is routinely described as particles communicating faster than light, or as mysterious spooky connections, borrowing Einstein's famous dismissive phrase. These descriptions are not just imprecise. They are misleading in ways that obscure the genuine strangeness of what entanglement actually is. Two particles are entangled when their joint quantum state cannot be factored into independent states for each particle. This sounds technical, but translates into something concrete. If you measure one particle, the outcome of that measurement is correlated with the outcome of measuring the other, even if they are separated by vast distances, and even if the measurements happen at the same time, which relativity says should prevent any signal from traveling between them. Bell test experiments have confirmed these correlations to extraordinary precision. The correlations are stronger than any classical probability distribution could produce, even if the particles had been allowed to share any amount of classical information before they were separated. The universe is not hiding a classical mechanism behind the quantum correlations. The correlations are genuinely quantum mechanical, genuinely non-local in a statistical sense, and genuinely incompatible with any local realistic description of nature. But, and this is the crucial point that popular accounts often miss, entanglement does not allow faster-than-light communication. When you measure an entangled particle, you get a random outcome. The outcome is correlated with what your distant partner will get, but you cannot control what outcome you get. There is no way to encode information in the randomness of quantum measurement results, so no information travels faster than light. What is non-local is the correlation, not any signal or information. This distinction matters for understanding quantum computing, because entanglement in quantum computers works in the same way. Qubits are entangled within the processor, and these entanglements are what create the correlations that allow quantum interference to amplify correct answers. But the entanglement does not enable any kind of faster-than-light communication between parts of the processor. It enables something different, a fundamentally richer set of correlations between the computational states than any classical system can produce. To understand why this is computationally powerful, consider an analogy. Imagine trying to solve a maze. A classical search strategy tries one path, hits a dead end, backtracks, tries another path. Each path is explored sequentially. A quantum strategy is different. The quantum state evolves as if it is exploring all paths simultaneously, with the amplitudes of dead-end paths canceling through interference, while the amplitude of the correct path amplifies. The quantum computer does not physically send a walker down every path. It maintains a superposition that encodes information about all paths simultaneously, and the interference between amplitudes acts as a kind of global information processing that has no classical analog. Grover's algorithm formalizes this intuition for database search problems. If you have an unstructured database of n entries and are looking for one that satisfies some condition, a classical computer must, on average, check n divided by 2 entries before finding it. Grover's algorithm on a quantum computer finds the solution in roughly the square root of n steps. For a database of 1 million entries, a classical computer checks about 500,000 entries on average. Grover's algorithm checks about 1,000. For 1 trillion entries, classical needs 500 billion checks on average. Grover needs about 1 million. This is a quadratic speedup rather than the exponential speedup of Shor's algorithm, but it is unconditionally proven. The Grover speedup does not depend on mathematical structure in the problem. It applies to any unstructured search, and it is optimal. It has been proven that no quantum algorithm can search an unstructured database faster than the square root of n by a result called the Bennett-Bernstein-Broussard-Vazirani theorem. The optimality result is itself illuminating. It shows that quantum computing is not magic. It has provable limits as well as provable advantages. There are things it cannot do faster than classical computation, and mathematicians have proven rigorously which things fall in which category. The theoretical study of quantum complexity, the quantum analog of classical computational complexity theory, is a mature and rigorous field, not speculation. Understanding these limits is important for calibrating expectations. Quantum computers provide exponential speedup for period finding, which enables factoring and discrete logarithm computation through Shor's algorithm. They provide quadratic speedup for unstructured search through Grover's algorithm. They provide exponential speedup for simulating quantum systems. Beyond these major classes, the landscape of quantum speedups is more varied and less fully mapped, with ongoing research identifying new algorithm families and new problem structures that quantum mechanics can exploit. One active area is quantum machine learning. Classical machine learning, the family of techniques underlying modern artificial intelligence, from image recognition to language models, involves training models on large datasets by optimizing parameters to minimize error. Some of these training algorithms involve operations on high-dimensional vectors and matrices that quantum computers might, in principle, accelerate. Quantum machine learning algorithms have been proposed that offer potential speedups for certain linear algebra operations central to machine learning. However, the practical relevance of these speedups is contested. Classical machine learning has access to enormous datasets stored in classical memory, and reading that data into a quantum computer is itself a computational bottleneck that may erase the speedup gained in the quantum computation. The field of quantum machine learning is active and genuinely uncertain. Some researchers believe it will offer meaningful advantages for certain learning tasks. Others are skeptical that the data input overhead can be overcome. The situation illustrates how quantum computing advantages that are clear in mathematical models can be complicated by practical engineering considerations. A more grounded set of near-term quantum computing applications focuses on problems where the quantum processor itself generates the data, eliminating the classical to quantum data loading problem. Variational quantum algorithms are a class of hybrid quantum classical algorithms designed for this regime. They use a quantum processor to evaluate a quantum circuit whose output encodes properties of a physical or chemical system, then use a classical optimizer to adjust the circuit parameters to minimize an energy function. The quantum processor does the quantum simulation. The classical computer does the optimization. Each step is natural for its respective technology. The variational quantum eigensolver, developed in 2014 by researchers at Harvard, Google, and University of Queensland, is the best-known example. It estimates the ground state energy of a molecule, the lowest energy configuration of its electrons, using a quantum circuit that encodes a trial wave function and a classical optimizer that iteratively improves it. This algorithm is designed to run on near-term, noisy quantum processors, sacrificing some of the asymptotic efficiency guarantees of idealized algorithms in exchange for practicality on real hardware. Results on small molecules using variational quantum eigensolvers have been demonstrated on real quantum processors. The molecules studied so far are small enough that classical methods can also handle them, making the quantum results verifiable. The goal is to scale these demonstrations to molecules in the strong correlation regime where classical methods fail. The scaling behavior of variational algorithms on noisy hardware is itself an area of active research, with some theoretical and numerical evidence suggesting that noise may fundamentally limit their performance at larger scales. This last point, the possibility that noise fundamentally limits variational quantum algorithms beyond a certain scale, illustrates how much about quantum computing remains genuinely unknown. The field is not in a phase of calm engineering execution toward a known destination. It is in a phase of simultaneous hardware development, algorithm development, and theoretical analysis, with the different research groups reaching different conclusions about the relative tractability of different paths to quantum advantage. The intellectual dynamism of this moment is one of the things that makes quantum computing such a compelling area of science to watch. The questions being asked are deep. The experimental tools to probe them are rapidly improving. And the answers will matter not just for technology, but for our understanding of physics, mathematics, and the nature of information itself. Information, it turns out, is not an abstract concept floating free of physical reality. Information is physical. This principle, articulated most sharply by Rolf Landauer at IBM Research and developed further by Charles Bennett, connects the thermodynamics of physical systems to the logic of computation in ways that have profound consequences. Landauer's principle states that erasing a bit of classical information must dissipate at least a minimum amount of energy, the Landauer limit, into the environment. This is because erasing information is an irreversible operation that decreases entropy in the computational system, and the second law of thermodynamics requires that entropy increase must occur somewhere. When information is erased, that entropy is dumped into the thermal environment as heat. At room temperature, the Landauer limit is about 2.8 times 10 to the negative 21 joules per bit erased. This is an extraordinarily small amount of energy, far below what actual processors dissipate in practice, where energy is wasted in resistive heating and switching delays. But as transistors shrink and densities increase, dissipation per operation decreases, and at some point, the fundamental Landauer limit becomes relevant. Quantum computing offers a partial escape from this constraint. Quantum gates are inherently reversible. Unitary quantum operations do not erase information. They transform quantum states in ways that can always be undone. A reversible classical computation, one that does not throw away intermediate results, can approach the Landauer limit arbitrarily closely, and quantum computation is inherently reversible in its gate operations. The energy dissipation in quantum processors comes primarily from measurement, from decoherence, and from the control hardware, not from the logical operations themselves. This connection between thermodynamics and computation is not just theoretically interesting. It has practical implications for understanding the ultimate energy efficiency of quantum hardware and for thinking about what physical resources are fundamental to computation. The laws of thermodynamics set limits on how efficiently information can be processed, limits that apply to quantum processors just as they apply to classical ones, though in different ways and at different scales. All of this, the thermodynamics, the complexity theory, the algorithms, the hardware, the applications, converges on a single observation that keeps recurring throughout the study of quantum computing. The universe is a quantum mechanical system. Its deepest level of description is quantum mechanical. Information encoded in quantum systems follows quantum mechanical rules. A computer built to exploit those rules has access to computational resources that have no classical analog. Classical computing is, in a deep sense, a subset of quantum computing. Every classical computation can be run on a quantum computer, with each classical bit replaced by a qubit initialized in a definite state. The quantum computer does not gain any advantage running classical computations. The qubits never enter superposition, and no quantum interference occurs. But the fact that classical computation is a special case of quantum computation means that quantum computers are, at the level of abstract computation, strictly more powerful than classical computers. They can do everything classical computers can do, plus additional operations that have no classical equivalent. This does not mean quantum computers will replace classical computers. Engineering, economics, and physics all conspire against that outcome. Quantum processors require extraordinary infrastructure to maintain. Classical processors can run at room temperature on relatively simple hardware. For the vast majority of computational tasks, the ones that do not involve factoring large numbers, simulating quantum systems, or searching large unstructured spaces, classical hardware is more practical, more efficient, and easier to scale. The future of computing is hybrid. Classical processors handling the bulk of computational work, quantum coprocessors handling the specific problem classes where quantum algorithms provide advantage, and the boundary between them evolving as quantum hardware matures and new quantum algorithms are discovered. This hybrid architecture will likely define the computational landscape for decades. Within that landscape, the most transformative early applications of quantum computing will be in quantum simulation and cryptography. Quantum simulation, because it represents the most direct expression of what quantum computers are naturally suited for simulating quantum systems. Cryptography, because the stakes are high, the relevant algorithms are well understood, and the transition to quantum-resistant encryption is already underway. Beyond these near-term applications, optimization and machine learning may offer more modest but still practically significant quantum advantages, particularly for problem structures that map well to quantum circuit designs. The landscape of quantum advantage for optimization is being actively mapped, and new problem classes are identified regularly. Further out, quantum network systems of quantum processors connected by quantum communication channels open possibilities that go beyond what individual quantum processors can achieve. Distributed quantum computation, quantum-secured communication between geographically separated processors, and eventually a quantum internet are directions that researchers are already exploring experimentally. Satellite-based quantum key distribution, demonstrated in orbit by China's Maishe satellite, is an early step toward global quantum communication infrastructure. The development of quantum networks also connects to fundamental physics in ways that are not purely technological. Long-distance quantum entanglement, maintained and manipulated across fiber optic cables or free-space optical links, tests quantum mechanics at scales and under conditions never previously accessible. Every quantum network node is an experiment in quantum physics, revealing how entanglement behaves under real-world conditions, how decoherence propagates through networked quantum systems, and how quantum repeaters can extend the reach of quantum communication beyond the limits set by photon laws and optical fiber. Quantum repeaters are a technology that does not yet exist in fully functional form. A classical repeater amplifies a signal, copying it and rebroadcasting it to extend communication range. Quantum information cannot be copied. The no-cloning theorem of quantum mechanics proves that making an exact copy of an unknown quantum state is impossible. Quantum repeaters instead use quantum teleportation and entanglement swapping to extend quantum correlations over long distances without copying. The protocols exist theoretically and have been demonstrated in small-scale experiments. Building repeaters that work reliably enough for practical long-distance quantum networks is an ongoing research challenge. It is worth noting how different the physics of quantum networks is from classical networks. Classical networks transmit information encoded in classical signals, electromagnetic waves, voltages, light pulses that can be measured, amplified, copied, and retransmitted at will. The information is public in the sense that it can be read without disturbance. Quantum networks transmit quantum states that cannot be copied or measured without disturbance. Eavesdropping on a quantum channel leaves detectable traces. The quantum internet, if realized, will be not just faster or more secure than the classical internet, but physically different in the fundamental constraints on what information can be copied, shared, and read. This physical difference is what makes quantum cryptography unconditionally secure in a way that classical cryptography cannot be. Classical encryption is computationally secure. Secure under the assumption that certain mathematical problems are hard. If those assumptions are wrong, if a polynomial time factoring algorithm is discovered for classical computers, or if quantum computers become powerful enough to run Shor's algorithm on real keys, the security fails. Quantum key distribution is physically secure. Its security follows from the laws of quantum mechanics, which no computational advance can circumvent. The transition to post-quantum cryptography, cryptographic systems secure against quantum attack, is underway, but will take years to complete across the global digital infrastructure. The challenge is that the infrastructure is vast, deeply embedded, and dependent on cryptographic primitives that are in some cases baked into hardware that is expensive to replace. Even after the National Institute of Standards and Technology finalizes its post-quantum standards, updating the hundreds of billions of devices and systems that depend on classical public key cryptography will be a generational engineering effort. This transition is sometimes called the quantum apocalypse in popular writing, a phrase that conveys urgency while obscuring nuance. The threat from quantum computers to classical encryption is real, but not sudden. Quantum computers powerful enough to break real cryptographic keys do not yet exist and will not exist in their fully capable form for some years. The window for transitioning to post-quantum cryptography is open, and organizations with long-term security requirements, government agencies, financial institutions, critical infrastructure operators are already beginning the transition. The risk is not zero, but it is manageable with appropriate planning and prioritization. The more immediate concern is sometimes called harvest now, decrypt later. An adversary with access to encrypted communications can record ciphertext today and store it, with the intention of decrypting it once a sufficiently powerful quantum computer becomes available, potentially years or decades in the future. For data that will still be sensitive in 10 or 20 years, classified government information, trade secrets, health records, the harvest now decrypt later threat is real today, even though powerful quantum computers do not yet exist. This is why intelligence agencies and security researchers are pressing for urgency in the post-quantum migration that might seem premature to those focused on the current state of quantum hardware. The timeline for the threat is not the timeline for current quantum computers. It is the timeline for the data's sensitivity, combined with the timeline for quantum computer development. For long lifetime sensitive data, the threat is present. All of these threats, the physics, the algorithms, the hardware, the cryptographic consequences, the chemical simulation potential, the philosophical implications weave together into a picture of technology that is genuinely transformative in ways that are specific, real, and still substantially unfolding. Quantum computing is not one thing. It is a family of technologies, algorithms, and theoretical frameworks that share the common thread of exploiting quantum mechanical phenomena for information processing. The era of quantum computing is not arriving all at once in a dramatic moment. It is arriving in pieces, in specific problem domains, on specific hardware platforms, for specific applications, as the engineering matures and the algorithms develop. Each piece is real and significant. The full picture will take decades to come into focus. What is already in focus is the mathematics. The quantum advantage for factoring is proven. The quantum advantage for simulation is established. The no-cloning theorem and its consequences for quantum communication are settled physics. The connection between entanglement and computational power, while still being refined theoretically, is supported by decades of rigorous work. What remains uncertain is the practical question. How long will it take to build hardware capable of realizing these advantages at the scales needed for the applications that matter? The answer depends on physics, materials, science, engineering, ingenuity, and economic investment, all of which are evolving in ways that are genuinely hard to predict. The best available evidence suggests that fully fault-tolerant quantum computers capable of running Shor's algorithm on real cryptographic keys are likely at least a decade away, possibly significantly more. But near-term quantum advantages in simulation and optimization may arrive sooner, as hardware with hundreds or thousands of high-quality qubits becomes available within the next few years. The scientific community will continue to refine these estimates as hardware improves, as algorithms mature, and as theoretical understanding of quantum computational advantage deepens. The honest scientist does not promise revolution by a specific date. They describe the mathematical foundations, the physical mechanisms, the engineering challenges, and the directions of progress, and let those facts speak for themselves. Those facts say, quantum computing is one of the most consequential scientific and technological developments of the 21st century. Its mathematical foundations are among the deepest ever laid for a technology. Its physical basis is the best tested theory in the history of science. Its potential applications address some of the most important scientific and practical problems of our time. And its development is still in its early chapters, with the most important results likely still ahead. That combination, deep foundations, real potential, and substantial uncertainty about the path, is what makes quantum computing so compelling to scientists, engineers, investors, and anyone who cares about the future of knowledge and computation. The universe is a quantum system. We are only beginning to learn how to read it. There is one more dimension of quantum computing that deserves attention before this exploration concludes, and it is perhaps the most philosophically ambitious one. Quantum computing may eventually help us answer questions about quantum mechanics itself that have remained open for nearly a century. The measurement problem is the oldest and deepest unresolved issue in quantum mechanics. When a quantum system is measured, the smooth, deterministic evolution of its quantum state, described by Schrödinger's equation, gives way to a random, discontinuous jump, the collapse of the wave function into one of several possible definite outcomes. The probability of each outcome is given by the Born rule, the square of the amplitude for that outcome. This description works perfectly as a practical recipe for predicting experimental results. The Born rule has been tested to extreme precision in countless experiments, and it always works. But it is not derived from the rest of quantum mechanics. It is added as an extra postulate. And the process of measurement itself, what counts as a measurement, what causes the jump, whether the jump is a real physical process or just an update of our information, is not described by the theory. It is assumed to happen when observers interact with quantum systems, but quantum mechanics provides no microscopic description of what distinguishes a measurement from any other quantum interaction. Interpretations of quantum mechanics are different proposals for how to think about this gap. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, takes a pragmatic stance. The quantum state is a tool for predicting measurement outcomes, not a description of reality between measurements. Questions about what the electron is doing when we are not looking are, in this view, not meaningful scientific questions. The theory tells you what you will observe. That is all a physical theory needs to do. The many worlds interpretation, proposed by Hugh Everett in 1957, takes the opposite approach. It takes the wave function completely seriously as a description of physical reality and refuses to postulate any collapse. When a measurement occurs, instead of collapsing, the wave function branches. Every possible outcome occurs in a separate branch of reality. The observer and everything entangled with the measurement splits into multiple copies, each corresponding to a different outcome. The universe is constantly branching in this picture, but observers within any branch only experience one outcome and cannot observe the others. Many worlds is deterministic, unitary, and mathematically clean. It takes quantum mechanics at face value without adding collapse as an extra process. But it comes at the cost of an unimaginably complex ontology, infinitely multiplying branches of reality with no possibility of ever communicating between them. Critics argue that the many worlds interpretation does not derive the Born rule. It simply declares that probabilities are given by the squared amplitudes without explaining why rational observers should assign probabilities in that way when all outcomes occur. There are other interpretations. Pilot wave theory, developed by Louis de Broglie and later David Bohm, says particles always have definite positions, but are guided by a pilot wave that evolves according to Schrödinger's equation. The randomness of quantum measurement comes from ignorance of the precise initial position of the particle, not from any fundamental indeterminacy. Cubism says quantum states are not descriptions of the world, but descriptions of an agent's expectations, and the Born rule is a consistency condition for rational belief rather than a statement about physical reality. Each of these interpretations makes the same predictions for all currently feasible experiments. They are empirically equivalent with respect to everything we can currently measure. This is why the debate has persisted for nearly a century. There is, as yet, no experiment that would distinguish between them. Quantum computers may change this. As quantum processors scale up in size, maintaining coherence over increasingly complex systems, they create experimental regimes that probe the boundary between quantum and classical behavior in ways that smaller systems cannot. If quantum mechanics continues to hold perfectly in large systems, if superpositions and entanglements remain coherent over many hundreds or thousands of qubits undergoing complex quantum circuits, that is powerful evidence against theories that propose a physical collapse mechanism at some scale. Various subjective collapse theories, like the Ghirardi-Rimini-Weber model and Penrose's gravitational collapse proposal, predict that superpositions spontaneously collapse at a rate that increases with the size or mass of the system. A sufficiently large quantum processor maintaining coherence would rule out collapse rates above certain thresholds. Conversely, if the development of quantum computers runs into unexpected fundamental obstacles at certain scales, if there is a physical reason, quantum coherence cannot be maintained beyond some complexity threshold that is not explained by ordinary decoherence and engineering challenges, that would be deeply interesting data for the foundations of quantum mechanics. It would suggest that something about large-scale quantum superpositions is physically different from small-scale ones in a way not captured by current theory. This possibility sounds speculative, but it is taken seriously by some physicists. Roger Penrose, the Nobel Prize-winning physicist, has proposed that quantum superpositions of gravitationally distinct mass distributions are inherently unstable and collapse spontaneously at a rate related to the gravitational energy difference between the branches. This Penrose collapse mechanism, if it exists, would impose a scale limit on quantum coherence that would manifest as a fundamental obstacle to quantum computers above a certain size. The Penrose mechanism is not widely accepted in the physics community, but it is a testable prediction that quantum computing hardware is already beginning to probe. The intersection of quantum computing and quantum foundations is one of the most intellectually fertile areas in contemporary physics. The technology and the fundamental science are not separate pursuits. Building quantum computers requires such precise control over quantum systems that every engineering failure mode teaches physicists something about how quantum mechanics behaves in real physical hardware. Every improvement in qubit coherence times is an experimental constraint on theories of spontaneous collapse. Every demonstration of quantum interference in larger systems is a test of the limits of quantum superposition. This feedback between technology and fundamental science is one of the distinguishing features of the quantum era we're entering. Quantum technologies, quantum computers, quantum sensors, quantum communication networks are not just applications of quantum physics. They are experimental instruments for quantum physics, probing regimes of quantum behavior that laboratory experiments with individual particles never accessed. Quantum sensing, which uses quantum systems as extraordinarily precise measurement devices, is already providing practical applications alongside its fundamental physics contributions. Atomic clocks based on quantum transitions in cesium and strontium atoms are the most accurate timekeepers ever built, losing less than 1 second in billions of years. GPS satellites rely on atomic clock technology, as does the global financial systems transaction timestamping infrastructure. The navigation and communication systems of modern civilization rest on quantum mechanical precision. Quantum interferometers, devices that split a quantum wave along 2 paths and then recombine them using interference to measure tiny phase shifts, can detect gravitational waves, variations in Earth's gravitational field, rotational motion, and other physical quantities with precision far beyond classical instruments. Gravitational wave detectors, like LIGO and Virgo, which detected the first gravitational waves in 2015. Ripples in spacetime from colliding black holes a billion light-years away use quantum noise as one of their fundamental sensitivity limits and are being upgraded with techniques from quantum optics to push below that limit. The broader category of quantum technologies, which includes quantum computing but extends to quantum sensing, quantum communication, and quantum imaging, is generating economic and scientific activity on a scale that governments and private investors are recognizing as strategically important. The United States, China, the European Union, and several other nations have launched national quantum initiatives with billions of dollars in funding. The strategic stakes are explicit. Quantum computing, if it matures first in one nation's hands, could provide advantages in cryptanalysis, drug development, and materials discovery that translate into economic and national security advantages. This geopolitical dimension of quantum computing adds urgency to the technical work and creates both opportunities and risks. The opportunity is that substantial public funding accelerates basic research that might otherwise wait for slower private investment cycles. The risk is that overhyped projections, driven by the competitive pressures of demonstrating national programs' effectiveness, lead to misallocated resources and public misunderstanding of what quantum computers can actually do and when. Calibrated, honest communication about quantum computing's current state, its genuine near-term potential, and its longer-term possibilities is not just intellectually valuable. It is practically important for guiding research priorities, investment decisions, policy choices, and public understanding. The science is real. The technology is advancing. The timeline is uncertain. All three of these things are true simultaneously, and each needs to be communicated clearly for the quantum computing story to be understood correctly. The atoms in your body are quantum systems. The molecules making up the cells in your brain evolved over billions of years, driven by chemical reactions whose rates and products are determined by quantum mechanical interactions. The photons your eyes detect from this screen are quantum particles. The electrical signals propagating through your nervous system depend on ion channels whose gating is influenced by quantum mechanical effects. You are, in a meaningful sense, a quantum mechanical system. The computers we have built until now have been classical systems trying to model and exploit a quantum universe using classical rules. Quantum computers are different. They are quantum systems exploiting quantum rules to process quantum information in ways that classical rules cannot. They are, in a sense, tools more native to the deep structure of reality than anything we have built before. That is not mysticism. It is mathematics. The quantum world follows specific rules, described by specific equations, tested to specific precisions. Quantum computers follow those same rules, in controlled ways, for specific computational purposes. They are not windows into the supernatural. They are instruments tuned to the frequency at which the universe actually vibrates. What we will learn from building them, and what we will be able to do because of them, is one of the central open questions of 21st century science and technology. The answer is being assembled, qubit by qubit, algorithm by algorithm, in laboratories and server farms and university research groups around the world. The question is not whether quantum computers will be transformative. The physics says they will be, for specific, important problems. The question is the shape of that transformation. Which problems will yield first? Which applications will prove most important? Which hardware approach will scale most reliably? And what we will learn about the nature of reality in the process. Those questions are being answered right now by researchers doing some of the most intellectually challenging work in the history of science. Following their progress is not just watching a technology develop. It is watching the boundary of human knowledge move, at the place where the universe reveals itself most clearly to be not a classical machine made of definite objects following definite rules, but a quantum system of amplitudes and entanglements, probability and interference, where information itself is woven into the fabric of physical reality. Whatever quantum computers ultimately achieve, that is already remarkable. Consider for a moment what it would mean if we could fully simulate the behavior of electrons in a living cell, not a simplified model, not an approximation, an exact quantum mechanical simulation, tracking every electron's state and every electron-electron interaction in real time. The computation required is staggering beyond any classical hardware, but the question itself reveals something important about biology that is rarely discussed in popular accounts of life. Life is a quantum phenomenon, not in a vague metaphorical sense, but in a literal and increasingly well-evidenced way. Photosynthesis, the process by which plants convert sunlight into chemical energy, has been shown through ultrafast spectroscopy experiments to involve quantum coherence in the way energy moves through the light-harvesting complexes of green plants and algae. When a photon is absorbed, the excitation does not travel through the molecular system by random classical hopping from molecule to molecule. It travels as a quantum superposition. The excitation is simultaneously in multiple places, interfering with itself in ways that efficiently channel energy toward the reaction centers, where it can be converted into chemical energy. This quantum coherence in photosynthesis was controversial when first proposed based on experimental results in 2007. Some researchers argued that quantum effects at biological temperatures far warmer than the carefully controlled environments in which quantum computers must operate could not survive long enough to play a functional role. Subsequent experiments have refined the picture. The details of how quantum effects contribute to photosynthetic efficiency in warm, noisy biological environments remain a subject of active research, but the basic observation of quantum coherence in biological light harvesting is solid. Similar evidence has emerged for quantum effects in bird navigation. Certain migratory birds can sense the direction and inclination of Earth's magnetic field with extraordinary precision, enabling long-distance navigation that classical mechanisms do not adequately explain. The leading proposed mechanism involves cryptochrome proteins in the bird's eyes, where pairs of electrons formed by light absorption remain in a quantum-entangled radical pair state for long enough that the Earth's weak magnetic field can influence the ratio of two chemical products, creating a chemical signal that encodes magnetic direction. The radical pair mechanism, initially developed theoretically and then supported by experimental studies on birds and isolated cryptochrome proteins, is one of the most striking proposed examples of functional quantum mechanics in biology. Enzyme catalysis, the process by which proteins dramatically accelerate chemical reactions, also shows evidence of quantum effects. Hydrogen atoms, being the lightest atoms, have wave functions that are spatially extended enough for quantum tunneling to matter in some enzymatic reactions. Quantum tunneling allows a hydrogen nucleus to pass through an energy barrier that it classically should not be able to cross, significantly speeding up certain reaction steps. Kinetic isotope studies, which compare reaction rates using hydrogen versus deuterium, the heavier isotope, provide experimental evidence for tunneling in several enzymes, including alcohol dehydrogenase. These examples of quantum biology are relevant to quantum computing, not just as additional evidence that quantum mechanics matters in practical contexts, but because they illustrate the same fundamental point. Biology has been exploiting quantum mechanical phenomena for billions of years, through the evolutionary process of natural selection acting on molecular systems. The quantum coherence in photosynthesis, the entangled radical pairs in bird navigation, the tunneling in enzyme catalysis, these were not engineered by physicists. They emerged from 4 billion years of evolution, optimizing molecular machines for function in warm, noisy, wet environments. Quantum computers must do something similar. Engineer quantum mechanical processes that function reliably despite noise, temperature fluctuations, and coupling to environmental degrees of freedom. The difference is that quantum computers need to maintain coherence for much longer, over much larger systems, and with much more precise control than any biological quantum system requires. Biology gets away with brief, localized quantum effects in small molecular subsystems. Quantum computers need to maintain global coherence across thousands or millions of qubits, requiring conditions far from biological norms. This comparison suggests both an opportunity and a challenge. The opportunity: studying how biological systems manage quantum effects in warm environments might provide inspiration for engineering more robust quantum hardware. The challenge: the quantum effects exploited in biology are not of the kind needed for general quantum computation. They are brief, purpose-specific, and embedded in a context that evolved to make them work. Translating biological quantum effects into engineering principles for quantum processors is far from straightforward. Nonetheless, quantum biology is a growing field, and its development is connected to quantum technology in important ways. Quantum sensing instruments built for quantum computing research, highly sensitive magnetometers based on nitrogen vacancy centers in diamond, for instance, are now being used to study quantum effects in biological systems at the single molecule level. Technologies developed to understand quantum coherence in biological contexts are informing quantum hardware design. The boundaries between fundamental biology, quantum physics, and quantum engineering are more permeable than they might appear. All of this points toward a broader truth about the scientific era we are entering. The 20th century was, in significant ways, the century of classical physics applied to engineering. The transistor, the laser, the atomic bomb, nuclear power, and the entire digital revolution emerged from applying 19th and 20th century physics to practical problems. The 21st century may well be the century when quantum physics not just discovered, but systematically exploited, reshapes technology in ways that are at least as profound. We are early in that process. The tools are primitive by comparison with what they will become. The understanding is incomplete. The engineering challenges are formidable, but the mathematics is real. The physics is real, and the potential is real. Every year brings new experimental demonstrations, new hardware milestones, new algorithms, new theoretical results, and new applications that researchers had not anticipated. The history of technology suggests that transformative technologies often look from the inside like they are taking forever, and then from the outside like they arrived all at once. The transistor was invented in 1947. The personal computer arrived 30 years later. The smartphone arrived another 30 years after that. Each step seemed slow in its own time. In retrospect, the pace was extraordinary. Quantum computing has been developing for 40 years as a serious scientific field. The first practical quantum algorithms were discovered 30 years ago. Experimental demonstrations on real hardware began 25 years ago. The technology is real, advancing rapidly, and built on some of the deepest physics ever developed. The next decade will see continued rapid hardware development, possibly the first demonstrations of quantum advantage on practically relevant problems, and the beginning of the cryptographic transition to post-quantum standards. The decade after that will see if the current pace of progress continues, and if no unexpected fundamental obstacles emerge, the development of fault-tolerant quantum computers capable of running Shor's algorithm on real cryptographic keys, quantum simulations of molecules in the strongly correlated regime, and quantum optimization algorithms applied to industrial problems. What comes after that is genuinely open. The history of computing suggests that the most important applications of a transformative computational technology are the ones nobody predicted when the technology was being developed. The creators of the transistor did not predict the internet. The creators of the internet did not predict social media. The pattern repeats. Transformative technologies create new capabilities that enable new applications, that open new problems, that drive new technologies. Quantum computers will follow this pattern. The applications driving the current investment in quantum computing, cryptography, chemistry, optimization will likely be among the first to benefit. What comes after, built on top of those initial capabilities, shaped by the new kinds of problems that quantum computation makes tractable, is not yet imaginable. This is not a reason to suspend critical judgment. It is a reason to follow the science carefully, to understand what the technology can and cannot do, to distinguish genuine milestones from hype and to maintain the intellectual honesty that allows for both excitement about real progress and skepticism about premature claims. The physics is compelling, the mathematics is profound, the engineering is hard, the applications are consequential, and the deepest questions about the nature of quantum measurement, about the physical limits of computation, about the quantum foundations of biological life remain beautifully, productively open. That openness is not a failure. It is an invitation. The universe has been running its quantum computation for 13.8 billion years. We are just beginning to learn how to read it. It is worth pausing on the specific mathematical structure of Schrödinger's equation, because it is the thread running through everything we have discussed, and understanding it intuitively clarifies why quantum computers are what they are. Schrödinger's equation describes how the quantum state of a system, its wave function, evolves in time. The equation is linear. If you have two valid solutions, their sum is also a valid solution. This linearity is the mathematical source of superposition. Any combination of quantum states is itself a valid quantum state. A particle can be simultaneously in a state of spin up and spin down. A system of 300 qubits can be simultaneously in any combination of all 2 to the power of 300 possible classical configurations. The equation is also unitary. It describes evolution that preserves the total probability. The sum of all squared amplitudes always equals 1. This means quantum evolution is reversible. Given the final state, you can always compute the initial state. No information is lost during quantum evolution outside of measurement. These two properties, linearity and unitarity, are what define quantum computation. Quantum gates are unitary linear transformations of the quantum state. Quantum circuits are sequences of such transformations. The computational resources available to a quantum computer are precisely the unitary transformations of the Hilbert space of the qubits. This mathematical structure has deep consequences. Because quantum gates are unitary, they are reversible. Every quantum computation can be run backwards. Because the space of unitary transformations on n qubits grows exponentially with n, the computational resources scale exponentially with the number of qubits. And because interference between amplitudes is built into the linear structure of quantum mechanics, quantum algorithms can use interference to concentrate probability on correct answers. This is not metaphor. It is the mathematics that underlies every quantum algorithm, every quantum cryptographic protocol, every quantum simulation. Schrödinger's equation is not just a description of atomic physics. It is the architecture of a computational paradigm. When researchers talk about quantum advantage, they are ultimately talking about a consequence of this mathematical structure. Problems whose solutions can be identified by exploiting the interference and entanglement available in high-dimensional Hilbert spaces have quantum algorithms that are faster than any classical algorithm. Problems whose solutions cannot be identified this way do not. The challenge of finding new quantum algorithms is the challenge of discovering new problem structures that quantum mechanics can exploit. The research frontier in quantum algorithm design is pushing in several directions simultaneously. One direction is variational algorithms, already discussed, which use parameterized quantum circuits to approximate solutions to optimization and simulation problems on near-term hardware. Another is quantum walks, generalizations of classical random walks to quantum mechanics that have been used to design quantum algorithms for graph problems and element distinctness. Another is quantum linear algebra, which uses quantum amplitude amplification to speed up certain matrix operations relevant to machine learning and numerical simulation. A particularly active frontier is quantum algorithms for differential equations. Many physical systems, fluid dynamics, heat diffusion, electromagnetic fields are described by partial differential equations. Solving these classically on fine-grained discretizations requires enormous memory and computation. Quantum algorithms for linear differential equations, particularly the HHL algorithm published in 2009 by Harrow, Hasidim, and Lloyd, offer exponential speedups under certain conditions. The conditions are restrictive. The speedup applies when the solution can be encoded and read out efficiently, conditions that do not always hold in practice. But the algorithmic ideas have stimulated a productive research program exploring which classes of differential equations admit quantum speedups. There is also growing interest in quantum algorithms for problems in combinatorics, graph theory, and number theory beyond factoring and discrete logarithm. The hidden subgroup problem, a general mathematical framework that encompasses factoring and discrete logarithm as special cases, has quantum algorithms for abelian groups, but not yet for non-abelian groups in general. Solving the non-abelian hidden subgroup problem would immediately yield quantum algorithms for graph isomorphism and other problems in combinatorics, but the challenge has resisted solution for 3 decades despite sustained effort. The search for new quantum algorithms is in some ways a mathematical problem as much as a computational one. It requires identifying structural properties of problems that quantum mechanics can exploit, and then constructing quantum circuits that exploit those structures efficiently. This is creative mathematical work, not engineering. The algorithm is discovered through mathematical insight. The implementation is an engineering challenge for hardware and compiler teams. All of these threads, from the physical hardware challenges to the mathematical algorithm design, from the near-term applications to the long-term fundamental physics implications, converge on a single coherent story. Quantum computing is the technology of exploiting quantum mechanics for computation, and it is maturing along multiple fronts simultaneously in ways that make the next decade one of the most consequential periods in the history of computation. The science fiction version of quantum computing, a black box that instantly solves all hard problems, is wrong in important ways. Real quantum computing is specific, mathematical, constrained by physical engineering challenges, and limited to problem classes where quantum mechanical structure provides genuine advantage. But the sober, accurate version is not less impressive than the science fiction version. It is more interesting because it is real. Real quantum computers will factor the numbers protecting global communications. Real quantum computers will simulate molecules that classical computers cannot, accelerating drug discovery and material science. Real quantum computers will probe quantum foundations in regimes that laboratory physics cannot reach. Real quantum computers will be entangled with the deep mathematical structure of information, computation, and the physical universe in ways that no classical machine ever was or could be. That is not fiction. That is where the physics leads, and where the engineering is taking us. The universe began in a quantum state. The Big Bang was a quantum event, its details governed by quantum field theory and possibly quantum gravity. The evolution of the universe since then, at the level of atoms, molecules, and the elementary particles making them up, has been continuous quantum mechanical evolution. Life, intelligence, technology, all of it has unfolded within a quantum mechanical cosmos, exploiting quantum effects in ways ranging from the accidental to, in the case of quantum computing, the deliberate and mathematically precise. We are building machines that run on the same rules as reality itself, at the deepest level where those rules operate. What we learn from that about computation, about physics, about the nature of information will redefine what is knowable and what is computable for generations to come. Researchers working at the forefront of quantum computing today are navigating a peculiar position in the history of science. They are simultaneously engineers, physicists, mathematicians, and explorers. They are building devices whose operation requires maintaining some of the most delicate physical conditions ever achieved by human technology, to run algorithms whose design requires some of the deepest mathematical insight in the history of computer science, to solve problems whose practical importance could reshape medicine, energy, communications, and national security. The peculiarity is that they are doing all of this while the fundamental science they are exploiting, quantum mechanics, still contains unresolved conceptual questions that have been contested since its inception. They are building technology on foundations that are operationally complete and experimentally unassailable, but interpretively contested. The equations work perfectly. What the equations mean at a philosophical level is still argued over by serious physicists. This situation is unprecedented in the history of technology. Classical computing was built on classical physics, whose conceptual foundations had been sorted out over centuries and were not seriously contested by the time the first transistor was built. Quantum computing is being built on quantum mechanics, whose mathematical formalism is settled and extraordinarily precise, but whose interpretation, what it says about the nature of reality, remains an open question. There is something intellectually honest and even beautiful about acknowledging this. The machines we are building are more powerful in specific ways than any classical alternative. We understand mathematically why they are more powerful. We can demonstrate experimentally that they behave as the mathematics predicts. And yet, we do not have consensus on what the mathematics says reality actually is. Science progresses this way. Operational understanding outruns philosophical understanding. Tools enable discoveries that feed back into theoretical refinement, and the process never reaches a final endpoint where everything is understood. The history of physics is full of moments where tools built on incomplete understanding led to deeper understanding through use. The spectroscope was built before quantum mechanics existed, but the atomic spectra it measured provided the data that quantum mechanics was built to explain. Quantum computers, built on quantum mechanics, may provide the data that helps us understand quantum mechanics more deeply. This recursion is genuine. A quantum processor maintaining coherence over 1,000 qubits running a complex quantum circuit is a probe of quantum mechanics at a scale and complexity that no previous experiment has accessed. If quantum mechanics describes reality as well at this scale as at smaller scales, the measurements will confirm it. If not, discrepancies will appear that require new physics to explain. The technology and the fundamental science are not separate. They are part of the same ongoing inquiry. Research programs explicitly connecting quantum computing hardware to foundational physics questions are underway. Experiments designed to test objective collapse theories using quantum optomechanical systems, microscopic mechanical oscillators cooled to their quantum ground state, are attempting to probe whether superposition breaks down at mass scales predicted by Penrose-type collapse models. Experiments using quantum error correction to study thermodynamics of information are testing Landauer's principle at the quantum level. Experiments using quantum simulators to study quantum phase transitions, abrupt changes in the quantum state of matter at absolute zero, driven by quantum fluctuations rather than thermal fluctuations, are probing condensed matter. Physics in regimes inaccessible to classical simulation or simple, theoretical models. The scientific richness of the quantum computing research program, spanning from fundamental physics to applied engineering to pure mathematics, is one reason the field attracts such diverse and talented researchers. It is a field where a deep insight about the nature of quantum entanglement can be directly applicable to designing a better quantum error correcting code, which is directly applicable to building a more reliable quantum processor, which is directly applicable to running a molecular simulation that answers an important chemistry question. The intellectual chain from fundamental to applied is short and continuous. Students entering this field today will spend their careers in that chain, moving between fundamental physics, mathematical algorithms, hardware engineering, and domain applications as the technology matures and the science advances. The skills required span quantum mechanics, information theory, materials, science, cryogenic engineering, software systems design, and domain expertise in chemistry, biology, cryptography, or whatever application area they focus on. It is a genuinely interdisciplinary field, and interdisciplinary fields tend to be where the most interesting and consequential new ideas emerge. If there is a single takeaway from everything discussed here, it may be this: the quantum revolution in computing is not about speed in the simple sense. It is about the nature of information itself. Classical computers process information encoded in definite binary states. Quantum computers process information encoded in quantum amplitudes in the full mathematical richness of quantum state space, with its superpositions, entanglements, and interferences. The difference is not quantitative. It is structural, mathematical, and ultimately physical. The universe is described by quantum mechanics. Information in the universe is quantum information. Classical information is a special case of quantum information, just as classical computers are a special case of quantum computers. Building machines that process information according to the full quantum rules, rather than the restricted classical rules, is, in a profound sense, building machines that are more naturally aligned with the way the universe actually works. That alignment is what quantum computing's advantages come from, and it is what makes the field so scientifically significant, beyond any particular application or any particular hardware milestone. Quantum computing is not just a faster version of classical computing. It is a different relationship between computation and physical reality, one that is still being developed, still being understood, and still revealing new depths with every qubit added and every algorithm designed. The universe ran its first quantum computation at the beginning of time. We are learning to run ours now.